of Oxford, who will talk about axisymmetric solutions to the Navier-Stokes equations.
Okay. Thank you very much, Helen, for introduction, and thank you very much to organizers of this term and organizers of this workshop. This is the title of my talk, but if I'm going to talk about axisymmetric solution to the Navier-Stokes equation, it would be very, very technical and very boring talk, especially after talk of Thierry. It's so difficult to talk because he's a very excellent speaker. And also I want to relate my talk with the topic of this conference, with the turbulence. I'm not expert in the turbulence, and I spent 3 weeks before the conference trying to understand things. This is one point. Another point, that this year is 100th anniversary of Olga Ladezhinskaya, and I am collecting some opinion of other mathematician about her opinion about other mathematician, and it turns out to be that a lot of opinion about her connected with the turbulence. And the first example of this, it was I was invited to a workshop dedicated to the memory of Yudovich. It was something like 2006 or 2007. I don't remember exactly, but there was Arnold was there, and he had some kind of a preliminary talk or forward, and in this there are many things were in his talk, but for me important thing was he somehow split mathematicians who are trying to understand turbulence in two groups. One group was, in one group there were Ladezhinskaya, Leray and Ladezhinskaya, and they thought that, but this is Arnold, of course. Think about they thought that turbulence is because of singularities. Since you have singularities for Navier-Stokes equation, this is a cause for turbulence. While Arnold saying that it is another group of mathematicians, like Arnold himself, Yudovich and Kolmogorov, thought about this as a phenomena instability. So you have dynamical systems. In this dynamical system, you may have instability, and this creates so-called, which I don't exactly understand, kind of deterministic chaos. I myself, I knew Ladezhinskaya from 1985, something like this, and she all the time saying that it is very complicated, that turbulence is because of very complicated system. You have instability, you have to study attractors, so it's not exactly what Arnold said about here. But it was words, and I decided to find some kind of publication where something was written in this sense, and I found the book recollection book dedicated to the 80s of Arnold, and in this book is unfortunately in Russian. I couldn't find English translation, but there are people who understand this Russian in this room, and they of course confirm that my translation is okay. But translation is saying that in 60s, many expert mathematicians, including Leray and Ladrzyńska thought that turbulence is caused by non-uniqueness. Now it's not singularities, but non-uniqueness. And they were against of his idea about instability, about that the turbulence is called instability. So about Ladrzyńska, of course, I don't know. I know her from as I told, from 1985, and all the time she's saying that turbulence is because of the very complicated dynamics, and there were examples like strange attractor of Lorentz or two-dimensional Navier-Stokes equation. So it's not clear for me. And as to Leray, I never met Leray. I couldn't exactly to know what Leray thought about this. But Arnold, of course, was a student, was a student in Paris and attending lectures of Leray. Now I decided to look what Leray said about this. And next page is from his famous paper 1934, and in this famous paper he just write down, I propose to say that it constitutes as a turbulent solution. And why there is a footnote, and footnote is as follows: I allow myself to cite a passage from Oseen. So it's not his opinion, but it's opinion of Oseen. And it is interesting to read this opinion of Oseen. This is a citation. From still another point of view, it seems that the trouble to subject the singularities of the motion of a viscous liquid to a careful study. If singularities appear, then we must distinguish two types of motion, of a viscous liquid, regular motion, which is to say motion without singularity, or irregular motion, which is, say, motion with singularities. Now, in other parts of hydraulics, one distinguishes two sorts of motion, laminar and turbulent. And one is tempted from now on to presume that laminar motion furnished by experiment identically to theoretical regular motions, and that experimental turbulence motion are identified with irregular theoretical motion. Does this preassumption correspond with reality? Only further research will be able to decide. So I don't see any serious claim from Leray saying that is turbulence really related either with non-uniqueness or singularities. Okay, in the same book or collection dedicated to the 80s of Arnold, there was a paper of Ilyushenko. Ilyushenko was a student of Arnold, and now is a big figure in Moscow mathematics. And he also had some kind of passage about turbulence. And in this passage, it was written something which is saying that, okay, Ilyushenko is very good specialist in dynamical system, but he is not very well understood Navier-Stokes PDE, because it's of course there are people who are doing analysis of PDE. I belong to the school. There are doing people which are doing dynamical system, which say producing this deterministic chaos, and sometimes there is misunderstanding. And for example, again, Ilyushenko things that Leray thought that turbulence is coming from the fact that there is a solution to the Navier-Stokes equation with sufficiently with very smooth initial data lose smoothness and became only continuous, and for them non-uniqueness is not maybe violated. So maybe you have non-uniqueness. To me, it is this statement is not correct. Saying that he doesn't understand very well analysis of PDE. Okay, so this is the foreword. Now I want to go to my talk, and the talk will contain some introduction, and we will see why I'm unhappy with the statement. All right. So what we have a many interesting mathematical problem related to the Navier-Stokes equation, and one of them, it's a global well-posedness. This is probably not the most important problem in this theory, but for mathematicians, it's a really interesting problem. And this is, in effect, philosophically saying that whether or not Navier-Stokes equation admit a deterministic description of the flow. That's what we wanted to prove, essentially. And if you look at the simplest problem, I'm not going to be in very detail about this problem because there was a very nice talk of Maria yesterday with very nice introduction. So we may consider Navier-Stokes equation in whole space for simplicity with these boundary conditions. For example, velocity goes to 0, as goes to infinity, and we have initial data, and we assume about initial data whatever we want. So we may assume that they're differentiable with any power, divergence free, and maybe with compact support. And the question is whether or not we have for this situation a unique solution to this problem. And here you have a viscosity, which is one parameter here, and we are asking this question for fixed nu. If nu is a positive parameter is fixed, then we can put it equal to 1. But in principle, there is another fundamental problem. How solution depends when as viscosity goes to 0. Okay, now, so what we know, essentially, the answer is yes, if you have two-dimensional case. It is for the Cauchy problem, it has been done by Leray, by complex analysis method, and by the kind of modern method, it has been done by Ladyshenskaya also many years ago using this Ladyshenskaya inequality. So this is not a question in dimension 2. In dimension 3, the situation is not clear. So what we have is a global existence of weak Leray-Hopf solution with initial data from L2. But however, it seems to be, and this is many people are completely sure that this problem is opposed with initial data from L2. And this you can as a kind of explanation to this, you can refer to the paper of J and Sverak, where you need if you put some spectral assumption, then you have non-uniqueness. You have instantaneous non-uniqueness with especially selected initial data with singularity 1 over x at 0. And this is, of course, not the full proof. There is a numerical analysis showing that it is true. So it is true. I think that it will be proved soon. And also, if we can refer to the talk of Maria Colombo yesterday, where this is also non-uniqueness takes place for forced equation. The forced equation is not included to a millennium problem, but anyway, it is still interesting question. And other things we know very well, it is a local in time well posedness for good initial data. So, what is another fundamental contribution of Jean Leray in the same old paper is the so-called, now we call this weak-strong uniqueness theorem, this theorem saying that if you have smooth solution, this smooth solution is going to be a unique in the class of Wigler-Hopf solution. So we have this principle for weak solution regularity implies uniqueness. And that's why people who are doing analysis of PDEs, it's just this is a business for them. You have a solution with finite energy, try to show that solution either smooth or it has some problem. So regularity implies uniqueness, and you can also reformulate this statement in this way. For Navier-Stokes, you have non-uniqueness might happen only due to appearance of singularities. So that is the way why we are hunting for singularities for Navier-Stokes equation. This is just the sign that maybe we will have non-uniqueness. Okay, so what does it mean, singularity? It's another point to discuss. My way of is due to Caffarelli-Kohn, Nirenberg in paper in 1988 about regularity of weak solution, Wigler-Hopf solution. And the definition is like this. The point Z0 in space-time, this is the point here, is a regular point of V if there exists a neighborhood, see, parabolic neighborhood, this is neighborhood, such that the velocity is bounded there. Okay, so Z0 is a singular point if it is not regular. So in other ways, if you point singular, then you have velocity unbounded in the neighborhood of this point. I remember that I discussed this maybe 10 years ago in Vienna. I gave a talk and saying what I think about singularities, and Uriel Frisch was in the room. And when I gave this definition, he said that it cannot happen. It completely lost interest to my talk. Okay, now what we know. This is, I'm still trying to have a bridge between in the previous bridge with the Arnold and Ladezhinskaya-Leray. Yes, singularity. You may think that singularity is very, if they are, that it's very, very conditional, therefore very unstable, and that's how you can join this two point of view. That singularity is also the reason for the turbulence, because it's very unstable. Probably, if you have it. So that is, now I want to go and to explain why I don't like the corresponding statement of Ilyushenko. So first of all, if V is bounded solution to the Cauchy problem, then it is unique and infinitely smooth. So boundedness, you have no choice, solution is very smooth. If the Cauchy problem is not uniquely solvable, you must have singular points. Somewhere velocity should go to infinity. In principle, so far we cannot exclude uniqueness of solution with singularities. So it's nothing. If you have energy solution, if it is unique, why we should care if it has singularity or not? Okay. Now, maybe Ilyushenko is right if you are saying about a local boundedness. Okay, in this local boundedness, you have the following thing. If you have Navier-Stokes as equation without any boundary and initial condition, if U is a bounded solution to the Navier-Stokes equation having finite energy, then we know if pressure is integrable with any power. I don't want to discuss this power 3/2 for the pressure. It's very reasonable, and I don't want to explain now. If it is so, then any special derivative is Hölder continuous in the neighborhood of space, in the half ball. Hölder continuous in space, any derivative in time. So there might be, if the velocity field is continuous, it might have, by this statement, it might have singularities in time only, not in space. However, so even in this statement, if you want to have such singularity, you need somewhere to have a real singularity in space-time, where velocity goes to infinity. So this is saying that Ilyushenko might keep in mind, actually not Navier-Stokes, but Euler. It's for Euler, we have this type of singularities when we go to viscosity goes to 0, you have a very, very big gradient. Solution itself is very smooth, but at the end you will have a solution of Euler equation with, say, bad Hölder continuous normal or derivative in space, blah, blah, blah. But it is completely different singularities. You don't have such singularities for Navier-Stokes equation, right? That's saying that Ilyushenko was not very good in understanding of analysis to the Navier-Stokes equation. Okay, now I want to go to actually to my talk, and my talk is a kind of local regularity theory. This local regularity theory for Navier-Stokes developed by actually Caffarelli and Nirenberg, based on fundamental observation of Vladimir Shevpak. So why we study local regularity? Because, you know, when we are doing elliptic or parabolic system, we know that they have this property of solutions, make it smoother without any relationship with boundary, what kind of boundary you have, what kind of smoothness of boundary condition, smoothness of initial. It's just the properties of Navier-Stokes equation as it is. Of course, it is not absolutely like for elliptic and parabolic equation, because Navier-Stokes are not completely local. Okay, so what is this main subject in this theory? Main subject is so-called suitable weak solution. Maria told about this suitable weak solution, but I want to emphasize that suitable weak solutions is just solution to the Navier-Stokes equation without any boundary condition, initial condition, just the solutions. And here is this definition, which is usual definition. You have a velocity having finite kinetic energy square integrable dissipation, satisfying Navier-Stokes equation and satisfying local energy inequality. Which you have this local inequality if you consider the parabolic system, usually 3 follows from 1 and 2, but not for Navier-Stokes. However, to consider such additional restriction is reasonable because if you have a solution to the initial boundary value problem, there is at least one solution which having this property at each point, at each subdomain. So that's why it's a special solution. You may think about that this is a solution, the only one, and you can study this. If you, for example, if you can construct solution which doesn't satisfy local engineering inequality, you have immediately non-uniqueness. So in this theory, the question is posed like this: you have a suitable weak solution in the parabolic neighborhood of given point Z0, and the question is whether or not Z0 or under which assumption Z0 is a regular point of V. That is, there exists a parabolic neighborhood of this point where solution is bound. So this is the question like this, what we are studying. And since Navier-Stokes is special, but still having the same features as nonlinear parabolic system or elliptic system, and for them it is very well known that you have a kind of partial regularity theory, and something like this should also be available for Navier-Stokes equation. And there are two types of statement, and this is called epsilon regularity theory. One statement is on a particular scale. If you have this functional, if this sum is less than epsilon, then you have in the half ball you have any spatial derivative which are continuous in space and time. And you also have nice estimate for the V. You also have the same estimate for the gradient. They are scale invariant, very nice. There is another statement is on small scales. When you compute the limits of certain quantities, here is this quantities, this is scale kinematic energy, this is scale dissipation. If this quantity is sufficiently small, Z0 is a regular point. So this is another type of regularity. And heuristically, all this regularity results can be expressed in the following way. We know that Navier-Stokes having this scaling, that is invariant with respect to the scaling, and theorem saying that if you have all these quantities are scale invariant, if you have a scale invariant quantity sufficiently small, you have regularity. That is now a theorem. Okay, but then you can classify singularities. If Z0 is singular point, then this value, of course, must be a positive, because if it is 0, it is less than epsilon, you have regularity. So if Z0 is singular point, all these limits, minimum of them should be strictly positive. And then we define the type 1 blow up if G of Z0 is finite, and type 2 if this G0 of Z0 is equal to infinity. So this is the different type of blow up. Well, what we can say about type 1, in type 1, it's easy to check if this guy is bounded, then all scale invariant quantities are bounded. So that means that we put on our equation assumption which makes this critical, because Navier-Stokes is supercritical. There is a fight between viscous part and convective part. Under critical assumption, the viscous part and convective part more or less in equilibrium. And that's then you somehow you are working with Navier-Stokes as it is a critical equation, which is you can use a lot of technique for such a type of investigation of type 1. Okay, now go to the aim of my talk. This is actually symmetric solutions, and here is the definition of axially symmetric solution. All the derivative with respect to the polar angle and cylindrical coordinate must be equal to 0. Usually we replace ball by cylinder, circle cylinder. And the question is the same. You have V and Q suitable weak solution in this canonical domain, and our question whether or not this point is going to be a regular point or not. And we have an answer to this question. It is a swirl. If swirl is 0, then you have Z naught as a regular point. It was proved by Kang and Vladimir Sverak in this local statement, but for the Cauchy problem, it was proved many years ago by Ladizhinskaya and in competition with Zhukovsky and Udovich. So what happens if swirl is 0? We don't know. And our conjecture, this is going to be a theorem, is saying that if Z is a singular point of V, then it should be type 2. So that's saying that singular point in axisymmetric case, there is no type 1 blow up. So it is somehow related with if you have singularity for axially symmetric solution, it must be somehow related to a dominance of convective term. Right, and in particular, type 1 exclude all this singularity which are very close to self-similar. It cannot happen for axisymmetric solution. Okay, so again, I recall you that if this type 1, then all scale invariant quantities are bounded, and this is important. So now about known cases. Well, first of all, there are so many papers on regularity for axially symmetric solution. If I started to list them, there will be I will finish exactly to the formal dinner today. So I'm going to only to talk about those who are related with what I'm going to talk about. And this known cases due to Chen, Strain, Tsai Yao, Koch, Nadirashvili, myself, Vladimir Sverak, it's around, it's many years ago. It's saying that if you have axially symmetric solution satisfying this inequality, in this inequality, x dash is a distance between point x and axis of symmetry, and then Z naught is a regular point. So this is the kind of, if it is singularity, it's removable because of this assumption. It is, of course, a scale invariant assumption. Why it is related with the theorem or conjecture I stated before, because it is easy to check if this is true, then it must be blow up of type 1, which in the definition I gave. So this is the particular case of what I'm going to discuss. Now, nowadays, this particular statement is not very complicated to prove, and I give you here the outline of the proof just to get a flavor, what kind of mathematics we are going to use to prove it. And this is from my paper with Vladimir Sverak. So if you have this assumption, which is was written in the previous slide, then you, roughly speaking, you may say that in the neighborhood of this point, there is no type 2 at all. So all the points, if they're in the neighborhood of 0, all the points are more or less, if there is singularity, there should be type 1. Right. So that's exactly expression of this. So, and then we can reduce everything to the case alpha is equal to 1. This can be done by scaling and regularity, regularity for axially symmetric solution in annulus. In annulus, it's more or less two-dimensional Navier-Stokes equation with variable coefficient, nothing serious. And then you, using this simple theory, you can get estimate for this in terms of function or variable for which are quantities which are scale invariant. If they are bounded, then this guy is bound. So at the end, we have a particular case with this behavior near axis of symmetry. We have also things related with the swirl, which is bounded. This can be proved by a Moser iteration technique, or if you are working with initial boundary problems, then it can be done by maximum principle. And once you have this scale invariant quantity, you can look at this point through the zoom and reduce everything to Liouville type theorem for bounded tension solution. There should be axially symmetric solution. So if you do this, then you can show that if you have singularity, then there should be non-trivial solution of this equation, which we call ancient or backward, because time is going in opposite direction. It is going to be bounded. It has some decay, and it is actually symmetric and having these properties of the swirl. This is Liouville type theorem saying that this must be equal to 0, and therefore you don't have singularities, and you are, this is a way to prove this result. General result also can be proved in this way, but it is a bit more complicated, and I'm not going to discuss this today. This also can be reduced to Liouville type theorem. What is now the question is what happens if you what about the type 2? So it is okay. Sorry, I forgot to say that from this immediately follows that if you have axially symmetric solution in critical spaces, then they must be a smooth. And this is the list of critical spaces. In the first two spaces, you don't need any assumption about symmetry of solution. This just immediately you get smoothness. But in this L3, BMO minus 1 and BMO minus 1 infinity, you can show that if you have this non-bounded and solution is actually symmetric, it must be a smooth. Okay, so now there is further more recent results about slide supercriticality. So what is a slide supercriticality? It is kind of slow growth of critical quantities. They are not necessary to be bounded, but they can grow slowly. And this is started with a very nice paper of Pan. He considered it Cauchy problem in whole space are 3 times minus 1, 0, which is exactly under the my image. And he considered it this type of assumption. And this type of assumption, if you multiply everything by r, then r times the velocity is a critical value. And it is allowed to grow very slow in logarithmic way. So the point of this slide supercriticality is experience saying that if you have something critical, you can add to this critical logarithmic factor, and the result's still okay, but you have to pay a very big price. It is very technical to show that you have regularity. This is exactly the case and the case. And what Pan did, he proved that this value related with swirl has a logarithmic modulus of continuity, and then this plus result of step one gives you a theorem. It's roughly very rough. So the main point is proving this modulus of continuity for this function. So it's actually, this is subcritical. So you, from slightly supercritical, you go to a subcritical. And so if you know about regularity of this guy, then there are some papers saying that if you have this type of modulus of continuity or this type of modulus of continuity, then you have a full regularity. So the only thing you have to take care, this is about modulus of continuity rho times V5. And what my aim is here is make it completely local without any boundary, without any Cauchy problem, because I think that it should be a completely local stuff. So we consider this anything in the standard parabolic cylinder and trying to understand whether the origin is a regular point. And the theorem which I'm going to prove is saying that if those scale invariant quantities here and here, they're scale invariant, can grow slowly, very slowly, because alpha is very small and you have two logarithmic, then you have a regularity. This is the theorem A, and this theorem about saying that if you have V and Q axially symmetric solution and this two conditions above hold, then the origin is regular point. So what is the point in the proof of this theorem? In the proof of this theorem, you actually have a scalar equation for the swirl. And this scalar equation is nothing but heat with very singular drift. And that you need to prove that the solution of this equation has some delicate properties. If you just attack this problem as itself, this is just the linear problem with bad drift. Without any connection with the Navier-Stokes equation, it would be hopeless. But we can use the result from the epsilon regularity theory by Caffarelli-Kohn-Nirenberg. We can say from the very beginning, so we know some information about the sigma. And this information is as follows. So there is a set of bad points as sigma, which has Hausdorff dimension less equal to 1, maybe less than 1. All the singular points are on the axis of symmetry because x dash is equal to 0. And if you subtract this closed set, this set is closed, then any spatial derivative of V is Hilbert continuous. This follows from the Caffarelli-Kohn-Nirenberg. And some other simple stuff follows from this equation because you need to know something about derivative in time and derivative in space of this function sigma. So from the space W1P, where two derivatives in space, one derivative in time, summability with P. And also sigma goes to zero if you go to the axis of symmetry for almost all x3 on the axis of symmetry. That's what we have for free from the partial regularity theory. And this statement about the modulus of continuity of this function gamma is here. So this is the oscillation of function in cylinder of radius r is estimated through the oscillation in cylinder bigger. And this factor is showing what kind of continuity near the axis of symmetry you have. This is not exponential. This is not polynomial, but this is better than any logarithmic factor. Right. So this proposition is, as I already told you, a central one, and it can be improved, and it has been done by Taiping Tsai and his colleagues slightly later. Improvement was about, you can replace 1/4 by some parameter tau between 0 and 1, and consider other scale invariant quantities. Just the if you understand how it works, you can do. Comments on the proof. In some sense, this is a big deal. I mean, to prove this result is a big deal because you need to use a specific of your equation. Of course, it is used specific, but at the end, this specific should be closed by some argument from the general theory, which is argument in the George style, Ladezhinskoye-Uraltsev style, with a lot of technique. And I'm afraid that this is not a good place to discuss this type of proof here in this workshop. So anyway, it can be done. It can be done, and what I wanted to say, well, the technical things where we lose everything. It's we have this estimate for oscillation, which is more or less important part of the whole the George procedure is that this beta is bad thing that this beta is going to 0 when r goes to 0, and therefore for the normal situation you have an estimate from below and you will get a Hilbert continuity. But since it goes to 0, you can get, instead of Hilbert continuity, logarithmic Hilbert continuity, if you wish. And the last thing I want to say that you can get a similar result as a Pan result from this. If you just take this type of estimate for the velocity field, you can see that you have a very slow growth of scale invariant quantities. Therefore, this is more general than the result of Pan. So I think I should stop at this point. Thank you very much.
Okay, just to try to follow all the case that you raised, I have a very naive question. Do you include in your hypothesis that 0 is an isolated point?
No, no.
And so then the next question follows, what will be the result if you assume that the solution goes to the time 0, because you're looking at the past, to a situation where only 0 is an isolated point. Here, are the results simpler or not?
From the general,
Does it become trivial or what?
I don't think there is no difference.
There is no way of.
There is no difference. Either if you have regularity, of course, it is immediately kill all the points. But if you have if your point is the limit, as I could understand, you wanted to say that is the limit of other bad points. Nothing.
Because more or less I tried to connect with what Roman said about singularity for Euler, that if they happen, they have to be really disorganized in some sense.
Well, I already
so the
told you.
most simplest organized will be 1 point.
I already told you that is a huge difference between Navier-Stokes and Euler. People, I don't know exactly if there are people doing talk about Euler and they are hunting for singularity. All the time asking, what kind of singularity you are studying? And nobody tell me exactly what kind of singularity.
More questions?
So Gregory, is there any way to quantify your result in the same way you quantified Sverak-Serogin result for L3? So if you have a singularity, for example, can you prove that your scaling invariant norms or quantities are actually blowing up in maybe some monotone way or at some rate?
Yeah, I understand. Yes. You mean this tau result about the quantifying? This is actually the same spirit. You add to the critical stuff to something logarithmical. And of course, you can do this, but I never thought about that in this way. Just I'm doing it my way.
More questions? Comments? Okay, then let's thank Gregory and do break for lunch.
Thank you.